Let's see how LPS Solve API helps us in identifying the solution of LP problem. And I have listed some of the documentation that may be helpful, although all the information to solve an LP problem using R is in this lecture. If you need any more details, you can use these links to get that information. We are given that we have to maximize z is equal to x plus y, and the constraints are 50x plus 24y is less than equal to 2400, 30x plus 33y is less than equal to 2100, and we have to produce a minimum of 20 of x and minimum of 5 of y. So x is greater than equal to 20 and y is greater than equal to 5. This is where the code starts. So we first have to call the library LPSolve API in our namespace. Define a variable, I'm calling it as my LP model, and assign the value of an empty LP model. So in order to do that, you will call make dot LP and then pass in the parameters 4 and 2. I said 4 means that we have 4 constraints, 1, 2, 3 and 4, and 2 is that these constraints are dependent on 2 variables x and y. Next step is we have to load column 1 and 2 for the 4 constraints. In order to do that, we say set dot column and then we pass in the model, and then we say column number 1 and the values are 50, 30, 1 and 0 corresponding to x values. So 50 in constraint 1, 30 in constraint 2, 1 in constraint 3 and 0 in constraint 4. Similarly, we say the second column, we need to set the column of my LP model, column number 2 with values 24, 33, 0 and 1. So these are corresponding to y values in 4 constraints. So 24, 33, 0 and 1. 24, 33, 0 and 1. Next, we will set the objective function. And to do that, we say set dot objective function my model, and then the values of objective function of x and y are 1 and 1. Next, we define the constraints operator directions. So we say set the constraint type of my LP model, and they are less than equal to, less than equal to, greater than equal to, greater than equal to, corresponding to the first constraint, the second constraint, the third constraint and the fourth constraint. So after we have defined the directions, now we have to define the RHS value. So we say set dot RHS, again our model, my LP model, then concatenate 2400, 2100, 20 and 5 corresponding to 2400, 2100, 20 and 5 for the 4 constraints. In order to make the model more clear, we will give the names of our model using dim names, and we give it row 1, row 2, row 3, row 4, and our columns are x and y. And then we also define that this model is a maximized model, and then we print my LP model. So let's see what happens when we run this much code. So I'm going to copy paste this code and paste it in my R console. You can see that our model is listed here with objective function row 1, row 2, row 3 and row 4, and we have to maximize it. Let's look at the code next. Next is I simply run the command solve, and to do that I type in solve and it returns the value 0. That means the model was run successfully. And next step is I get the values of objective function, and when I do that I get 66.45161. Next I print what are the values of our variables x and y. So I say get variables of my model, and they are 30.9677. Finally, let's print what we termed as the sensitivity. So I'm going to say get me the sensitivity of the objective function. So it's get.sensitivity.objective and then the model reference, and I print that on the screen. We get objective from objective till. So x can range from 0.9090 till 2.0833, and y can range from 0.4800 and 1.1000. To get the sensitivity of right hand side values, we say get.sensitivity.RHS for our model, and I print that on the console, and I get 3 rows of output on my screen. So in order to make our discussion more easier, I have transferred the output from R into this Excel sheet, so it'll be easy for us to relate to the discussion. Here is the output from R, and the objective function maximized at 66.45, and I have that value here, and then the x and y variables are 30.96774 and 35.48387. I have them here, and the coefficient of x was 1 and coefficient of y was 1. And then we got that the sensitivity of the objective function shows that x ranges from 0.9090 to 2.0833, and I have that here, and the y ranges from 0.48 to 1.10, and I have that here. If we change the value of x or y one at a time, and we assure that the range of our values, the new value of x or y, is between this range for x and this range for y, then our optimal solution will still fall at x and y. However, the optimal objective value will change. So let's give it a try. So we know that we can change the value of x from 0.90 through 2.083. So I'm going to pick up 1.3. So I'm going to go to my code, and I am going to change that my x objective value is 1.3. Then I'm going to run my code again and get the output. And here is the output. So what we have is the objective value, optimized objective value is 75.749194. So I'm going to take this here, and we get objective value as this, but our x and y are 30.96774 and 35.48387, which is same. So now I'm going to do a test where I'm going to go beyond the given range. So I'm going to go 2.09 as x. So I'm going to go back to my code and change x to 2.09, and then I'm going to run this, and we see that our objective value, optimized objective value, is 100.304, but our x and y have changed. It is 45.6 and 5.0. So clearly, as long as we stayed within the range, the value of x and y stayed the same, the optimal objective value changed, but as soon as we went beyond the range, the value of the optimal x and optimal y changed, and the optimal objective value also changed. You can actually test the same thing with y as long as you keep the value of x as 1. So similar to the sensitivity for the objective function, I am going to transfer the output of sensitivity of RHS into Excel sheet to make our discussion easier. And first I'm going to take the output of duals, and I am focusing on row number 1 and row number 2, which are our limiting constraints. And for that, row number 1 we have 0.00322580 as dual, and I have transferred it here for row number 1. And similarly for row number 2 it is 0.02795, and I've transferred it here. And then the duals from value is 2.90909 into 10 raised to power 3. So I'm just going to take 2090.9 in Excel for row number 1 is dual from, and dual still is 3.345 into 10 raised to power 3, which is 3345. So I have it here. And similarly for row 2 I have it 1533 and 2525. So I have it 1533 and 2525, and this is the same output from optimal objective values and objective variables. So what this means is that for constraint number 1, if we modify our right hand side value to any value within this range, for every 1 unit increase in right hand side value, the improvement in the optimal objective value will be given by 0.00322. Similarly, if we reduce the right hand side value by still staying in this range, then the optimal objective value will reduce by 0.00322,581. Same thing if we keep the right hand side value what was original, but if we want to change the right hand side value of constraint 2, every unit increase in right hand side value, optimal objective value will increase by 0.0279, or every unit decrease while staying in this range, the optimal objective value will reduce by 0.02795. Let's do a quick test. I'm going to change the right hand side constraint for constraint number 1 from 2400 to 2401 and then run the code. So I have 2400, I'm going to change it by 1 unit, and here is the output. So if we look at this, our objective value has changed to 664584, and I have changed this to 2401. This is still 2100. Let's see what is our output of x and y. 31.03, and so now let's see how much did the optimal objective value change. So that means the difference between the new value and the original value is 0.00323, so which is 0.00322 rounded off. So it is clear that within this range, if every 1 unit increase of right hand side value of constraint 1 will change the optimal objective value by this number. You may want to notice that unlike the sensitivity of coefficients of objective function, in this case the x value and the y value change as well. So in this case we change x, we change y, and optimal objective value However, x and y still are forming the bases. So why is this important? This can be translated as every one additional resource of constraint 1 brings you the profit of 0.00322 units of production in this case.